Two trains leave towns 1,668 miles apart at the same time and travel towards each other. One train travels 18 miles an hour slower than the other. And if they meet in 6 hours, what is the rate of each train? Now remember, when you have problems like this, there's no way you're going to read it one time, immediately set up and solve the problem. You're going to have to read it several times and unpack what information has been given to you, and then try to figure out what exactly you're trying to find. So this is a motion problem. And one thing we're assuming in this problem is that the trains are traveling at a constant rate. So when we're talking about a constant rate, we know that the distance the object can travel is found by multiplying the rate of the object times how long the object has traveled. So that means distance equals rate times time. Sometimes we call this DIRT. Distance equals rate times time. So I would recommend that you pause the video, read it again, and draw yourself a little diagram. That's what I'm going to try to do. We have the first town, I'll call it just town 1, let's say, where the first train is. Luckily, I'm not going to be judging you on your artistic ability. There's my train, and that train's going to be going this direction. And then it says we have a second town, so I'm going to come over here and call this my second town. And the second train is at the second town. There we go, going toward the other trains, so they're going toward one another. And it tells us that the two trains are leaving towns that are 1,668 miles apart. So that's going to be the total distance from town 1 all the way over here to town 2 that's given to us. And important as you read the problem to realize that the first train is not going to be traveling all the way from town 1 to town 2. It's not going to travel an entire distance of 1,668 because it's very specific in saying that the trains are going to meet, and they're going to meet in 6 hours. So each train is going to travel a different distance, but together the total distance between the towns is 1,668 miles. Now, what we're looking for, and I always recommend that you highlight what you're being asked to find, that's our unknown. And our unknown is going to be the rate of each train. So I don't know the rate of the trains, so I'm going to go ahead and give that a variable name, and it would make sense to call that R if we're using R for rate. So I'll let R be the rate of the first train. So my first train is the one that's starting at town 1. And then it does say that one train travels 18 miles an hour slower than the other train. So even though I don't know the rate of the first train, I could come up with an expression to represent the rate of the second train because it's 18 miles an hour slower. That would mean I would take the rate of the first train and subtract the 18 miles per hour, and then that would equal the rate of the second train. So I'm going to call my rate of the second train R minus 18. So that's kind of a good setup. And anytime I have a distance equals rate times time problem, I like to set these problems up in sort of a grid that helps me get organized. Now, each row in this grid represents the motion of one of the trains. So I'm going to label. My first row is going to be discussing all the information about train 1, and then the second row in this grid is the information about train 2. So let's fill in what we know. We know that we called the rate of the first train R, so I'll just put R here in the rate column. The second train's rate was R minus 18, so we can go ahead and fill that in as well. Now for the time, remember, it says that the trains are going to meet in 6 hours. That's the time. So that's going to be the time that each train has traveled. They both have traveled 6 hours when they meet. So these are both going to be 6. Now, the distance is what I don't know as well. I'm not sure of the distance that each individual train has traveled. Be careful, because there is a tendency for people to want to put 1,668 here, and that is not going to be correct. Because remember that 1,668 is the total distance. So let me go back to my picture for a second. You know, train 1 leaves town 1 and travels this direction. And that train is traveling faster. So let's say they meet. Let's just pretend in my picture that they meet here. So the first train will travel a longer distance than the second train because the second train is traveling at a slower rate. So imagine the second train, let's just say, is like that. So when you take a look at the distance, which I'm going to highlight in yellow, that the first train has traveled, so the first train has traveled this distance here in yellow, that is not 1,668 miles. That's going to be less than 1,668 miles. And then same thing with the second train. If I highlight the distance that the second train has traveled, let's say in green, once again, that's not going to be 1,668. So don't fall into the trap of putting 1,668 in your grid for D, because that's the total distance. So you could go ahead and just call the distances D, because we don't know how far they've traveled. But you do have to be careful with that as well, because if we call both of the distances D, then that implies that both of the trains have traveled the same distance. But again, look at my picture. The yellow highlight here, this yellow highlight is definitely going to be longer than the green highlight because the first train is traveling faster. So one way of doing this, and there's many ways, I'm just showing you one. One way would be to use a subscript here. And let's say I call the first train's distance D1 and the second train's distance D2. So I'll label that again on my diagram. That would mean that this yellow distance is D1, and then my green distance, the distance that the second train has traveled, would be D2. So what you can see then is if we were to add these two distances together, then they would equal the total of 1,668 miles. So that means that D1 plus D2, the distances that each train has traveled, when put together, will equal the total distance, 1,668 miles. Now, when we take a look at the motion equation, distance equals rate times time, I put it in this grid because we know that the distance will always equal whatever the rate of the object is multiplied by the time. So this is just sort of a nice way, I call it dragging out the equation for the first train. The first train's distance, D1, is equal to its rate times its time, which is in this case 6. That's R times 6. And if you reorder that, because most of you probably like to put the coefficient in front, that means D1 is equal to 6R. Let's do the same for the second row. The second train's distance, D2, is equal to its rate, R minus 18, times its time, which is also 6. Once again, most of you probably want to reorder that and put the 6 in front. So 6 times the quantity, R minus 18. So you have these two equations that represent the individual distances, and now you know if you add them together, it's going to equal 1,668. So D1, which is equal to 6R, will get added to D2, which is 6 times the quantity, R minus 18, and that equals the 1,668. So now we have a great algebraic equation to solve. The hard part's over. Now let's just do our algebra. So distributing 6R plus, we get 6R, and then 6 times 18 is 108, equals 1,668. We'll combine like terms, 12R. We'll add the 108 to the other side, which should give us 1,776. And then finally divide by 12, which leaves us with an answer of 148. Now think about your variable key. R was a rate, in this case a speed, so this would be 148 miles per hour. Now that's going to be the rate of the first train because again, looking at our variable key up here, R was the rate of the first train. Now the problem asks for the rates of both of the trains. So again, looking back at your variable key, we said that R minus 18 was the rate of the second train. That was the slower train, the one that was traveling 18 miles per hour slower. So then we would just need to subtract 18, 148 miles an hour minus 18 miles an hour will give us 130 miles per hour. So the second train's rate is 130 miles an hour. So we have found both trains' rates Clearly, these are some high-speed trains, so maybe we're in Europe somewhere traveling on a train, and the first one is traveling 148 miles an hour. The second is traveling 130 miles an hour.